What do I look like?
Nice.
Yeah. Okay. Well, there I am. Got my baseball cap on. All right. John Anderson just sent an email about you, Rob.
Ooh.
Yeah, we'll check that out later. All right. Well, whoops. Jeez Louise. Group chat got too big. All right. Class 4, here we are. Live from Memphis, Tennessee. So I have nobody with me today. I just have my rock star and then some kind of juice drink over here. So today we have a lot to cover. So we're going to go over, kind of the same format that we did before, but for those of you who haven't been through this before, this is going to seem like just a fire hose of information. If it doesn't already, it's going to be more. So I'm going to kind of get going. I won't be able to go in depth really in many of the concepts today. So that's kind of good and bad. The good thing is hopefully there's going to be some questions that I can address for you guys offline or between classes. That's the good. The bad is you just don't have a lot of time. So let's get going. So domain 2, we talked about asset security. Spent quite a bit of time talking about classifying data, and I give you some examples of really the real things that we use when we're working with clients to classify data. Went through this concept called ownership. We talked about different types of ownership. We talked about kind of the business ownership, the data ownership, and the system ownership, and how important those things are. Those are really core. Our profession in security, the only people who really do things are people that are kind of made to do things, unless you're the chief information security officer. But you can't do all this alone. So really defining and nailing down your roles and responsibilities around ownership is critical. Talked about memory and remnants last Tuesday, and we also talked about destruction and then some data security control. So those are the things that we went through on Tuesday, just to kind of refresh your memory a little bit. We're going to go through the quiz. So what I did for the quiz, I really took the quiz questions from the end of domain 2, and we can talk through those things. I do have chat up, so if you want to type in your answer before I show it, or if you have questions, I'd love to see those things. So we're going to start off with these 2 questions. I kind of have 2 questions per slide, so we'll go through it. What type of memory is used often for CPU registers? Is it DRAM, firmware, ROM, or SRAM? So 2 types of random access memory, the dynamic and the static, and then read-only memory or firmware. So the right answer here is D, SRAM, and watch this. Bam, just came out of nowhere. That D flew up from the bottom of the screen. I don't know if you guys saw that. That's the correct answer for CPU registers. If you remember where CPU registers are, they're very small, actually on the CPU, and very small storage spaces for really fast memory. The closer we get to the CPU, the faster the memory. So what type of firmware is erased via ultraviolet light? So there's 2 types of firmware we talked about last on Tuesday. One was erased by ultraviolet light, and the other one was erased with electric current. So the answers that we have is EEPROM, EEPROM, flash memory, and PROM. Prom. It's kind of prom time, isn't it? Like May? That's not the right answer. EEPROM, right?
Yep.
The electrically erasable, whatever. I couldn't say it on Tuesday. I probably can't say it much today either. Question 3, what describes the process of determining which portions of a standard will be employed by an organization? There were 2 kind of towards the end of that chapter, and these are terms that I had mentioned we don't really use in this context very much. And those 2 terms were scoping and tailoring. Baselines and policies, if you remember baselines is just really setting, usually we use that in relation to like a configuration, like a baseline configuration. It sets something that I can measure deviations from. So that's where I would use a baseline. Policies are governance documents, mandatory governance documents, high level, that kind of outline the roles for the organization. Scoping and tailoring were those two terms. Scoping is the right answer here, where I'm just taking portions of the standard. The tailoring is modifying the standard to fit my, fit my needs. So that's 3. Any questions so far? Basic, everybody's got those right. Number 4, what non-volatile memory normally stores the operating system kernel on an IBM PC compatible system? Disk, firmware, RAM, and ROM. So really one of those isn't even memory. Firmware really isn't memory. It's what's written to memory. RAM is volatile memory, so it's either got to be disk or ROM. And we'll go over this today too. Where the kernel is actually stored is on disk. Part of the power on self-test is to load that kernel from disk. So A is the right answer there. So disk is non-volatile. Store the swap file there too. So that's it. Number 5, what was ISO 17799 renamed as? It became 27002 is the right answer here. 27002 2005 :2005 is the first kind of renaming, and then 2013 is what we're using today. Which of the following describes a duty of the department? Patch systems, report suspicious activity, ensure their files are backed up, ensure data has proper security labels. A is a custodian role or responsibility. B is a user responsibility. So it's either got to be ensure their files are backed up or ensure data has proper security labels. Those would both be, I think, correct, but I think the best of those two is D. So 6. On to 7. Which control framework has 34 processes across 4 domains? Well, it's only one of these, and it's COBIT. So that's B. Which phase of Octave identifies vulnerabilities and evaluates safeguards? Phase 1, 2, 3, or 4, and I can't even remember off the top of my head myself. Good. You guys all have to know it for the test. There's 3 phases to Octave, and I mentioned, I think in class on Tuesday, that there's a 4th phase version of Octave. That's that standard from Carnegie Mellon. Which of the following is the best method for securely removing data from a solid state drive that is not physically damaged? That's important to note. If it was physically damaged, you just physically destroy the media. The best of these answers is the ATA secure erase. A. I don't know if I should give you guys more time to answer or not. The release of what type of classified data could lead to exceptionally grave damage to national security? Confidential, secret, secret but unclassified, and top secret. So if you're to put those in order to be top secret, secret, confidential isn't a national security, or is it? Oh, maybe it is. It's top secret, D. And there's actually, I don't think I mentioned on Tuesday, there's a clearance that only the president has. That's the highest level, and I don't know what it's called. But he gets a briefing every day with his kind of an aggregation of a bunch of top secret data. So number 11, a company outsources payroll services to a third-party company. Which of the following roles most likely applies to the third-party payroll company? Data controller, handler, owner, or processor? Anybody have a guess on this one? This is D, data processor. They're just processing the data. Which managerial role is responsible for the actual computers that house data, including the security of hardware and software configurations? So we talked about the different types of owners here. This would be the system owner, D. So far, I think we're doing pretty good. 12 out of 12. That's good. What method destroys the integrity of magnetic media, such as tapes or disk drives, by exposing them to a strong magnetic field, destroying the integrity of the media and the data it contains? Bit level override, degaussing, destruction or shredding. It looks like user and Jordan got this one right. It's degaussing or degaussing. I don't know how to say it the right way, but that's the answer. What type of relatively expensive and fast memory? So we know that that's going to be close to the CPU. Uses small latches called flip-flops to store bits. DRAM, dynamic random access memory, EEPROM, SRAM, or SSD. So two of those are not, anyway. So you have an SRAM. I don't know if that's a C for this answer. SRAM, C. Oh, I clicked in the wrong spot. So the DRAM was the one that uses the capacitors. It has to be consistently recharged. EEPROM and SSD are non-volatile. What type of memory stores bits in small capacitors? Like, I just told you the answer. This would be DRAM. So there you go, 15. Piece of cake. Looks like a good piece of cake. All right, so that was a quiz. That was easy, I think, fairly easy. If you've read along and kind of been following along, maybe looked at the notes from last class on Tuesday, that should all be pretty straightforward. And like I said, I think I warned you the very first class, a lot of this stuff is going to be memorization. If you don't work with these things on a regular basis, like for me, for instance, I don't work with any of the security models, very few of the security models we're going to talk about today. So for me, it's going back and really memorizing those things again so I can talk about them. You may find that you have to do a lot of that, kind of throughout the whole course. So here's just some current events. Most people heard about and have been hearing about. It's kind of been beat up hard, but it's still continuing. The Clinton emails, about the classification of those emails and whether or not she had broken the law or what have you. But that's a direct tie-in to data classification. There were even some emails that were just deemed too sensitive to even share in the Freedom of Information Act requests. The Panama Papers, that one's kind of seems like it's kind of flown under the radar a little bit, but this is a bunch of really damaging papers that were exposed recently. It affects a lot of the heads of state throughout the world. So there's a couple of things with this data in terms of maybe we shouldn't even have had that data anymore. Maybe it should have been subject to some data retention schedule, and we should have destroyed that data in some way. But certainly there's some security implications. It's an interesting story if you're looking for something to read. And then that last one, Centene, some missing hard drives, personally identifiable information for 950,000 people. Had that data been encrypted, then you wouldn't really have much of an issue, or if you had destroyed them. So really the best practice for data destruction would be to overwrite that media or degauss it, do something like that, and then store it securely until you have a chance to physically destroy. And then when you physically destroy it, get a certificate of destruction so you have a fully auditable process so things like that don't happen. Any questions? Easy stuff. You guys heard about any of these news articles? questions on the quiz. Today we're going to cover these things. We have probably 80-ish slides to get through tonight, so it's going to be a fire hose. There's going to be a lot of things today that you'll have to memorize for the exam, but then you can almost immediately just purge it. A lot of the security model things that we're going to talk about, you just don't use them. They're more conceptual. Today we're going to get up as far as we're going to go is we're going to go into virtualization and distributed computing, because as I went through preparing for the class today, there's just too much information, I think, to go past that. But that's okay, because after today's class we're not going to have any quiz or anything like that, and we've got a weekend, so we should be able to pick right back up again on virtualization and distributed computing, and then carry us right through. We'll have cryptography and physical security. I kind of don't like how they reorganized this domain in the common body of knowledge. This used to be 3 separate domains. Security architecture would take an entire class to talk about, cryptography would take an entire class and a half, and physical security would take an entire class. So what we need to do is kind of drive through all of those in 2 classes. So it's going to be a lot of information. But it's all good stuff too. It's all stuff that you will certainly be on the exam. It's all testable things. So certainly memorize it. So security models, back to our foundational concepts that we talked about with subjects and objects. So security models really define what security or what subjects and objects are permitted to do within a framework or within a model. And that's what a security model is. Subject, which we've talked about before, is an active entity in the system. Oftentimes that's a user, but it could be a process, could be a program, could be a service, could be any number of things. For the purpose of security models, at this point, we're going to really just focus on the user part of subjects. And then objects are the resources, passive resources. When you think through security models, certainly some of the first mandatory access control models we're going to talk about, it's important to kind of keep in your mind this read up, read down, or read down, write up. Read up, write down, and then the opposite. Because that's going to tell you if this is an integrity model, or if I tell you that it's an integrity model, you'll know that there's no write up, no read up. Wait, there's read up, but don't write down for an integrity model. So we'll talk about those things, concepts to remember, and there's just a diagram there. But we'll dig through these. There's really 4 basic types of security models that you need to be aware of. The first is discretionary access control, and it fits along with, it's discretionary. So the subject can, if they have the right privileges and the right permissions, can assign permissions to somebody else at their discretion. So that's what makes it a discretionary access control model. Windows, Active Directory, and Windows 2008, 2012, Windows XP, all those are discretionary access control models built into those systems. Linux is also a discretionary access control. Those are really easy for us to relate to. The mandatory access control systems, the rule-based access control systems, and even in the truest sense, the role-based access control systems, we don't work with those. Those are typically highly secure government-type systems where the access control policy is set up by the administrator, and that's it. So there's no changing, there's no cascading access control or permissions set once the mandatory access control has been set. So the difference between mandatory access control and rule-based access control is really mandatory access control is more focused on the objects, whereas rule-based access control is more set on rules and things that I can do in the system. But they're very, very closely related. And then don't get confused with the RBAC for rule-based access control and role-based access control. In the exam, if they just say RBAC, they're going to be referring to rule-based access control, not role-based. So a lot of us refer to, like if I put users into groups and then assign permissions to groups, and I've assembled those groups based on system role or based on maybe job role, that's this same type of role-based access control. It's sort of like that, but it's not in its truest sense. But whenever we, work in security and we talk about, how you're managing access control, if you're doing it that way, we usually interpret that as role-based access control. Hopefully that helps and I didn't confuse the matter too much. But these are the four types of access control models: discretionary, mandatory, rule-based, and role-based. These are all of the fundamental concepts or the security models that we're going to go through. So state machine, Bell-LaPadula, Lattice-based access controls, BIBA. Bell-LaPadula and BIBA are kind of counter to each other. They're kind of opposites. And so in the exam, those are kind of the two big ones too. I think the ones that might be covered the most in the exam. We don't use them in real life, really. And the way to remember the difference between Bell-LaPadula and BIBA is BIBA's got an I in it, so that's an integrity model. Bell-LaPadula is the confidentiality one. So Bell-LaPadula is really built to protect confidentiality. BIBA is meant to control or protect integrity. But we'll also go through Clark-Wilson, the information flow model, Chinese wall, which is the Brewer-Nash model, Take-Grant model, access control matrix. We're pretty used to the access control matrix, really it's just a table where you've got objects on one side, subjects on the other, and then permissions. The Zachman Framework for enterprise architecture, it looks really cool. It's very complicated. The Graham-Denning model and the Harrison-Russo-Ullman model. So just memorizing those names, I think, is tough. But memorizing what they all do is probably even tougher. So the first one is the state machine model, and this one, the way I remember the state machine model is if I have a system state, really a snapshot of the system, and I can validate and verify that system is secure. So that state is secure, and I'm in every transition that I make, every change that I make to that system is also secure, then the new state of the system will also be secure. So it's really about transitions of the state from one instance to another. And in this case, with respect to access control. So the state of the machine is captured in order to verify the security of the system. That's that first snapshot of the system. The state consists of all current permissions, all current instances of subjects accessing the objects, really everything around access control. So that first state, and then it always remains secure no matter what state it's in, as long as I'm following these rules. Now, for the purpose of the exam, that's essentially all you need to know for the state machine model. It's very basic kind of for everything else, though, as well. Let's go to the Bell-LaPadula. Bell-LaPadula is a confidentiality model. Let me move my thing so I can see what I had here. So confidentiality, so you can think of, when we talked about mandatory access control before, we talked about how subjects have clearances and objects have labels. So if I'm really concerned about confidentiality, then I shouldn't be able to read anything that has a label higher than my clearance, right? So that's the no read up rule. So if I know that Bell-LaPadula has to do with confidentiality, it's no read up and no write down. And the reason why it's no write down is if I have top secret clearance, you don't want me writing data down to to a secret levels, because that would also violate confidentiality. So no read up, no write down is how Bell-LaPadula works. Hopefully that makes sense. This one is very testable. Bell-LaPadula has been in the class material since the early 2000s when I took the exam, and it's still here. So originally developed by the U.S. Department of Defense, focused on maintaining the confidentiality of objects. And really the way this was, I think intended is if I'm out doing field work and collecting a bunch of information, and I need to report that to the central office or the headquarters, I should be able to write that data up. So it gets aggregated there. And I think, keeping that kind of compartmentalized so I can't take that data and write it down. That's where Bell Padula kind of came from. 2 access rules: the simple security rule, no read up, and then the star security property, no write down. Those are the 2 access rules. We have 2 object label rules. So access is really around the clearance and the label, but the labeling of the data, security labels will not change while the system is operating. That's the strong and weak tranquility property. And then the weak tranquility property is that security labels will not change in a way that conflicts with the defined security properties. So 2 access rules, 2 object label rules. That's Bell Padula. It's a confidentiality security access model. That's it. So you'll need to memorize this. Once you're done memorizing it and you pass the exam, then I doubt you'll use it. It's one of those things. But it's good conceptual. It makes you really think of data flows. Any questions on Bell Padula? To some of you, I might be speaking like an entirely different language. Lattice-based access controls, security controls for complex environments. You can see an example of a lattice and what it looks like on the top right of the screen there. This is another access. It's very complex. It's for a complex system. Things to remember about the lattice-based access control is that you have a least upper bound limit and a greatest lower bound limit. So it kind of keeps you in this range of access to objects based on your position in the lattice. It's all mathematical, so it's not like, if you're maintaining a system that's based on lattice-based access controls, that you'd diagram out your lattice, but yeah, that's lattice-based. So remember, for the lattice-based access control, that we have the least upper bound and the greatest lower bound. That's what defines my lattice for access control. BIBA. So BIBA is kind of the opposite of Bell Padula. The difference between BIBA and Bell Padula is Bell Padula was confidentiality. BIBA is integrity. And you can remember that again by the I in BIBA. And it works essentially the same way. So if I'm really concerned about the integrity of data, the no write-up principle means that I can't destroy or alter data at a clearance level that exceeds, mine. And I also can't. The read down, I don't think is quite as important in BIBA, but really it's all about integrity. The reverse of Bell Padula. All right. I want some questions. You guys should ask some questions, but maybe this is all like not question worthy. Clark Wilson, this is a real-world integrity model. Requires subjects to access objects via programs. So this really relies on the programs and how secure the program has been written to enforce the access controls. Programs have specific limitations to what they can do and what they can't do. 2 primary concepts: well-formed transactions. You'll see probably transformed procedures and constrained data items and unconstrained data items on the exam. If you see those things, you're talking about the Clark-Wilson model. This is essentially how the transactions, and the access controls are enforced through the applications. So comprised of access control triple, user transformation procedure, or TP, which is the well-formed transaction itself. Constrained data items. So the constrained data items are really what the transformation procedure applies to. The unconstrained data items don't require the data integrity, so they're not part of the model. And then integrity verification procedures just ensure that the data actually was manipulated the way it was supposed to. Valid. Separation of duties is also part of the Clark-Wilson model. Not quite as formal as it is in the Chinese wall model, which we'll talk about in a little bit. But we need to make sure that authorized users aren't changing the data outside of the applications. and that's Clark Wilson. Information flow model. Information flow model is not a model that, again, another one that I don't use very much, or if ever. But information gets compartmentalized, it gets put in its compartments, and we'll talk about compartmentalization a little bit. We mentioned it a little bit in Domain 2. We'll expand upon that a little bit more tonight. But when you talk about compartmentalization, it's really about the classification of the data, so the labels that are applied to the data, and then demonstrating a specific need to know. An information flow model is all built on those two factors. So subject clearance has to dominate the object classification. That means the label. It has to be at least as on the same level or greater. And the subject security profile must contain one of the categories listed in the object label, which enforces the need to know. So in each object, there are categories that are listed and maintained by the system. That's what enforces the need to know programmatically. And that's the information flow. Brewer-Nash, another model, also called the Chinese wall model, really meant to avoid conflicts of interest. It came out of financial services, and it was meant to keep consultants from, finding out information at one financial services institution and then taking that information and making decisions at another institution with confidential information. So prohibiting one person, such as a consultant, from accessing multiple conflict of interest categories. So the conflict of interest categories are assigned to the objects. And the enforcement is, I can't have these conflicting interest categories. Dynamically, depending on the user's previous actions, the model states that the subject can write to an object if and only if the subject cannot read another object that is in a different data set. Hopefully that makes sense. Initially designed to address the risks inherent in employing consultants working within banking and financial institutions. So if you hear Brewer-Nash, that's the one distinction from all others, is where it came from, and its purpose really is around conflict of interest, not so much access to data, just based strictly on confidentiality or labels or clearance levels. Non-interference models. So interference models. So whenever we see, I think it's supposed to be inference. Interference. Well, anyway, it's meant to stop inference attacks. Inference attacks are where I can look at a system, modify or monitor its behaviors, whether it be CPU cycles or electricity fluctuations, whatever, or maybe data put in swap files. Data gets paged back and forth. Whatever I'm using, but I can infer that what the data is based on other data around it. So it's really about guessing what's going on with the system, and that's what the non-interference models are made for. Covert channel is really a policy violation. So when I set up a system, I set it up with a specific security policy in place, certainly in a mandatory, these are all mandatory access control systems. And part of deploying a mandatory access control system is deploying the policy that's going to enforce security. So a policy violation that goes around those controls and hidden from the system owner would be a covert channel. And there's a number of covert channels. We'll talk about those when we talk about some of the attacks that can happen. So not necessarily concerned with the flow of data, but more what the subject knows about the state of the system. So like I was saying, observing a system, how it behaves from the outside without actually accessing data, and then try to infer what might be happening and try to guess. That's what the non-interference models are for. Take and grant model, govern the interaction between subjects and objects. So subjects have specific rules that they need to abide by when they're accessing objects. Two rights occur in every instance: take and grant. The rules take, grant, create, and remove. And those are what the rules are. So the take rule allows the subject to take rights from another object. grant rule allows a subject to grant own rights to another object. So this sounds like a lot like a discretionary access control system. Hey, a question. Awesome. How do you tell the difference between knowledge learned toward using data classifications Chinese wall? Not sure I understand the question. Not sure what you're asking there, Jim. The question is, how do you tell the difference between knowledge learned toward using data classifications Chinese wall? So I don't know if that's referring to an inference attack, if that's the knowledge learned. Anyway, I'll try to noodle that a little bit. So the grant rule allows a subject to grant own rights to another object. Again, this is a discretionary access control model. Create rule allows a subject to create new objects, and the remove rule allows a subject to remove rights it has on another object. That's the take grant. So just 4 simple rules in the access control model. Take and grant are the keys. Access control matrix. This one's really simple for us to understand because I think this is the one that we all kind of grew up with. Commonly used by operating systems and applications. It's very easy to understand. It's just a 2-dimensional database, really. So subjects are listed on one side, objects across the top, and then the types of permissions I have on each subject to the file. And so those are associated with the objects. And so when you try to attempt to access an object through the operating system, the reference monitor would be in charge of, the reference monitor is part of the kernel, and we'll talk about what the kernel here in a little bit. But the reference monitor would be responsible for looking up these permissions and allowing you to access or not access. The Zachman Framework for enterprise architecture. So 6 frameworks. You're not expect, so in any of these, and I'll go back to kind of when we started in domain 1. For the CISSP exam, you're not really charged with being an expert in any of these things. So you're not expected to know how to deploy, the Bell LaPadula access control model or security model in an environment. You need to know the basics. So the Zachman Framework is one of those things where I really just need to remember the basics. So 6 frameworks. It's the what, how, where, when, or who, when, and why. That's what you'll probably see on the exam, and that would tip you off right away that we're talking about the Zachman Framework. The framework on the right, that diagram, expands upon that a little bit more if you're interested in researching it. But that's really all you need to know for the Zachman Framework. Graham Denning, basic rights commands that a specific subject can execute on an object. 3 parts: objects, subjects, and rules. 8 rules, all the way from R1 to R8: transfer, grant, delete, read, create, destroy, create, destroy. Those are the rules for the Graham Denning. Harrison Russo Ullman model, HRU, operating system level, computer security model, deals with integrity of access rights on the system. So not the integrity of the object itself, but integrity of the access rights in the system. Based around the idea of finite set of procedures being available to edit the access rights of a subject on an object, maps subjects, objects, rights in an access matrix, variation of Graham Denning, so variation of our 8 rules. We have 6 primitive operations: create, create, destroy, destroy, enter write, delete write from the access matrix. So hopefully this is like one part of really the entire CISSP, where it's like it's so kind of foreign because we don't use these things every day, in our day-to-day job. But they're things that you have to memorize again, for the exam. But it makes it difficult to teach this particular domain just because it is so kind of abstract. We don't use it. Modes of operation, 4 modes of operation. The first mode of operation, so when I was talking about compartmentalized, that's going to be one mode of operation. Dedicated is another mode of operation. Mixed is another mode of operation. So the first one is dedicated. So dedicated, the important thing to remember about a dedicated system is there's only one classification, one type of objects. Well, not one type, but one classification of objects in the entire system. So I don't commingle secret and top secret. I don't commingle any different labeled data. It's all one label for the entire system. That's what makes it dedicated. So subjects, in order to access that data, have to have the right clearance level or greater. They also have to have a formal access approval. And I talked on Tuesday just briefly about a formal access approval. Whenever we see formal, that means documented. It needs to be supported by a process. And then 3, a need to know. So those 3 things are required for anybody to access a dedicated system. Very highly secure. That's a dedicated mode of operation. The next is system high. So system high contains a mix of labels. So I might have secret but unclassified, top secret, whatever. The subjects who are going to be accessing those systems have to have a clearance level that's equal to or greater than the highest object label. So if I have top secret, secret but unclassified, and public data on a system, for me to access that system as a subject, I would need to have top secret clearance. So that's the second mode of operation, dedicated, system high. The next is the compartmented. And we talked, I've mentioned it numerous times, but objects are basically placed into compartments. Subjects have to have a formal, system-enforced need to know to access. How do the security models come into play? Good question. Would you prescribe a particular module, or model, I'm assuming, if you followed ISO versus COBIT? It depends on the environment, but I would say in most cases, the mode of operation you'll use is multi-level. It's usually too costly to go with compartmented or system high or dedicated in private sector organizations, because then you have to buy separate systems for these things. So in most cases, in the private sector, you go with the multi-level in terms of the mode of operation. So compartmented, placed in the compartments. Formal system-enforced need to know access to the data in a compartment, as well as having clearance. So this is to the compartment, not to the system, like we had earlier. All subjects have to have a signed NDA for all information on the system. NDA would be part of that formal access approval, but not explicitly. 2, clearance for all of the information on the system. So again, like the system high, I might have compartments with different types of, or different labels for data. I would need to have clearance for the highest label for the system. Formal access approval for some of the objects on the system. So not everything, but certainly the data in the compartment that I need to access to. I would have to have a formal access approval for that, and then a valid need to know. Those are the things that would be required in a compartmented system. The fourth and final mode of operation is multi-level. So system contains objects of varying levels. Subjects with varying clearances can access the system. What mediates all the access is called the reference monitor. And we'll talk about the reference monitor when we talk about kernels and where kernels live in a little bit when we get deeper into the architecture. All subjects have to have a signed NDA for all the information, clearance for some of the information, formal access approval for some of the information, valid need to know for some of the information. So here we have all, some. Before we had all, some. So you have to have clearance for all the information in the system. What makes it different in multi-level is just you have to have clearance for some of the information on the system. Those are our 4 modes of operation. So far we've gone through like a ton of access, ton of security models, and we've gone through modes of operation, and it's only 7:45. That's a lot of things to memorize. And there's really, when you have things like this that you have to memorize, it's hard to really put it into context well. Like when you talk about Bell LaPadula, I can't give you really any good experience that I've had putting in or using a security model like that. So it makes it a little bit more difficult. This has been around forever. That's a picture, so that's just off of Wikipedia. That's the Rainbow series. So the Rainbow series is a number of different certification and evaluation and security audit control documents that were put together in the 80s. The two that we need to know, or at least know about for the exam, would be the Orange Book and the Red Book. The Orange Book is the Trusted Computer System Evaluation Criteria. It was originally developed and defined to evaluate products that we might put into our environment. And in this case, it would be the federal government. So there was guidance on what types of systems can be used for what types of information, what types of data, and we would use the Trusted Computer System Evaluation Criteria to do that. Developed by NCSC, which is part of NIST and the NSA. Developed in '83, so it's been around for a long time. It's not really used anymore, but it provided, I think, the foundation for future evaluation frameworks. One of the first, now used as part of, so it's changed quite a bit, but it's really more part of common criteria, which is another one of the evaluation criteria. So we have TCSEC and common criteria we'll talk about here in a little bit. These were the levels. You can download it at NIST, and I give you another link later on where you can get it in another form. So things to remember for the exam: if you see D, C2, B, B1, B2, B3, if you see these levels or divisions in the exam, you're talking about TCSEC or you're talking about the Orange Book. Just to give you an example, the highest, so and there we've got the discretionary access control, the mandatory protection, and the verified protection. Windows NT, so that kind of when this was being used, Windows NT was one of those that was evaluated against this. It was able to obtain a C2 as long as you didn't network it. So as long as you didn't connect it to anything, it could get as high as a C2 because it's a discretionary access control system. So we would never be able to apply mandatory protection to it. All of your Linux systems are, if they were going to be evaluated according to TCSEC, they wouldn't get to B. So the question in HIPAA. In HIPAA, want business associate agreement, what is the difference between BA and NDA? Well, business associate agreement is more specific to EPHI. An NDA is more of a blanket statement. You won't, according to the OCR, I don't think you'll be able to use an NDA in place of a BAA because a business associate agreement has a lot more prescriptive controls that have to be in place for the protection of PHI. So D, lowest, A, the highest. I don't know of any systems. I'm sure there are systems that have reached A1 verified design, but I don't know of any. And it's not used really much anymore. The other one is the Red Book. So the Red Book is the Orange Book for network systems. So think of the Orange Book as being just operating systems, typical server systems, things like that. The network systems, things that we put on the network, firewalls, things like that would be Red Book. You can download it there. The entire Rainbow series can be accessed there. You don't need to know for the exam and for like real life. I doubt you're ever going to use TNI to evaluate any systems yourself. But for the exam, understand that TNI is the Red Book in the in the Rainbow series, built kind of off of TCSEC, or very similar to TCSEC, which is the Orange Book. ITSec. So ITSec has kind of been replaced too now with, so there's three: TCSec, ITSec, and then the common criteria. Those are really the three evaluation methods or models that might be on the exam. ITSec really was an international evaluation criteria. It took the Orange Book and kind of expanded upon it and added some things. So it added a functionality and effectiveness and correctiveness. So if you look back at TCSec, this was really about assurance. The ITSec took an added functionality, which wasn't even part of TCSec, and then broke out assurance into two pieces, really: effectiveness and correctiveness, or correctness. These are the evaluation criteria or levels. So assurance correctness ratings range from E0, which is inadequate, to E6, a formal model. Functionality ratings range from TCSec evaluation, so F1 or FC1. F would be mapped to C1. F would be mapped potentially to C2 as well, but then we've got the additional criteria assigned, or additional ratings. Those are the ratings for ITSec. This is another one we'll just have to memorize. That's going to be kind of the key throughout this. At least when we get to encryption later on, there's some good functional controls that we can actually apply in our environment. Same with physical controls. Other things about ITSec, the additional functionality ratings. So when you look back, we added the functionality piece, the correctness, effectiveness and correctness. We've also, these are the functionality ratings. So high integrity requirements, high availability, so on and so forth. More memorization. That's kind of the key to tonight. Memorize, memorize, memorize. Common criteria is still used. Common criteria is also an international standard that's agreed upon. The US uses common criteria with kind of an ITSec spin to it. Describing the testing of security IT products. So I could, all of your, I think current IT products that, are used internationally have been probably evaluated against the common criteria. The primary objective for common criteria is to eliminate the known vulnerabilities of the target for testing, which leads us to these terms. So we have a TOE, a target of evaluation, the security target, which is essentially describing the target of evaluation. We have a protection profile, which are minimum requirements that need to be met or that will be tested against. Then we have evaluation assurance level, which is kind of the score at the end of it. So the target of evaluation, what am I actually testing? The security target, the documentation describing what I'm going to be testing, the protection profile, which is what I'm going to be testing this thing against. And you'll typically see that the protection profile would be applied across a class of systems or products. And then the score at the end of it gives me that EAL, which is the evaluation score. So this one I'm a little more familiar with because this one is still being used. 7 EALs, 7 levels of evaluation. AL1, functionally tested, all the way down to formally verified, designed, and tested, which is the highest. Very difficult, probably pretty expensive too, some of your EAL 7 things. The common criteria, there's the link there. If you want to read it, that's version 3. So if you see any of the EALs, so going back, if you see any of the EALs, you're talking about common criteria. It's used to evaluate products, security products, international. So that's that. We went through, like I said, we're going through kind of a lot now. We went through security models. We went through some evaluation things. We went through also modes of operation. So models, a bunch of them, about a dozen. We went through modes of operation. We had 4. And then we went through evaluation models, which there were 3. Actually kind of 4, because we talked about TCSec, we did talk about TNI, which was the red book, and then we briefly touched on ITSec and common criteria. So now we're going to transition from that into secure system design concepts. So this is kind of getting into the hardware of things and how those things are designed. The first concept mentioned is layering. For those of you, see, I grew up kind of a network guy, so when you tell me OSI as an example of layering, I can apply that, kind of right away. It's the same thing in hardware and software functionality, where there's some abstraction between the layers. So, and it's conceptual. There's nothing hard set that says that these have to be the layers. But in general, the generic list of security architecture layers are hardware, kernel, operating system, and applications. Hardware being the lowest layer, and then kernel being built on that, operating system being built on that, and then applications being built on that. And the concept is I can write an application, and I don't really have to care what happens at the hardware level as long as I'm writing the application for the operating system, because I'm only writing kind of to that closest layer, but it hides a lot of the complexity that goes on, lower down. That's one thing. And another thing is, if I write my application terribly, I shouldn't crash the entire system. It shouldn't affect the hardware layer. So that's kind of why we use this concept of layering. Separates hardware and software functionality into modular tiers. The tiers are separate from each other. Actions that take place at one layer don't directly affect components in another. For networking types, OSI is an example. So we've got the 7 layers of the OSI model, which we'll be talking about in detail. And I get excited about that one because it's where I grew up, is in networking. Generic list of security layers: hardware, kernel, operating system, and applications. That's the layering concept. Abstraction is really hiding the things that happen at the lower levels from the higher levels. So details about how, opening a Word document, all the things that go on between the operating system in finding where my file is, and then loading it into memory, and then associating the file with my Word processing program, and then executing that. All those things are really hidden from me as a user. All I did was just double click on the file. There's a good example. So early programmers had to control everything, even moving. Yeah, that's right, before abstraction. Same with networking. You kind of had to write everything into it. So abstraction is really nice. It allows developers to focus on more specialized parts of their program and not have to worry about all those nitty-gritty details. Makes the system a lot more stable, too. And I did mention, I think a couple of classes ago, how complexity really is the enemy of security. So the more complex we make things and systems, the harder they are to secure. Abstraction allows us to focus on different parts of the system and not overly complicate things. There's a good example in the book, and that's what's kind of written there, about a user opening an MP3 file and all the things that kind of go on, but at the end of the day, all you did is just press the play button. So that's abstraction. Abstraction is made possible through layering. And then security domains. So a security domain is a list of the objects that a subject is allowed to access. In a truer sense, it's a group of all the subjects and objects with similar security requirements into kind of a logical domain. The kernel, central core of the computer's operating system. The kernel is the core of the operating system. Every operating system has a kernel. 2 modes it usually operates in. It's either the user mode or kernel mode. The user mode is what the user is interacting with. That's where the applications are interacting. User accounts, processes all go through user mode. Low-level functions like hardware drivers, potentially. Some functions of lower-level applications. And the operating system itself really runs in kernel mode or supervisor mode. Low-level access to memory, not direct access to hardware, but basically. 2 domains are separated, so an error in user mode won't affect or shouldn't affect kernel mode operations. So if something goes wrong with my application, it shouldn't bring down the entire operating system. It shouldn't crash. It also there's this thing called the reference monitor, which runs as part of the kernel, which allows to kind of keep things separate. Operating systems run entirely in kernel mode. So domain, what a domain is, that concept I think is fairly straightforward and simple. A group of subjects and objects with similar security requirements, they all kind of play in the same domain. Kernels, two modes, and you'll have to know this for the exam for sure. User mode and kernel mode for the kernel, and what those two are. User mode, kind of higher level, kernel mode, low level. Operating system runs in kernel mode. The things that I interact with as a user of the system all runs in user mode. The ring model. So ring model is another conceptual concept. Sorry, I'm getting a cough here. This is CPU hardware layering. So there's 4 rings in x86 systems, Intel x86 systems. Ring 0 is the kernel, all the way up to ring 3, which is the user applications. Ring 2, device drivers, and ring 1, operating system components. There's actually they call it a ring -1, which is where hypervisor mode. So when you're running like virtual systems, the hypervisor supposedly runs 1 ring below. Again, this is all fairly conceptual. There's not a really strong delineation between the rings in a CPU. So processes communicate between the rings via system calls. System calls are typically slower, so if you can run things within a ring, it's faster. I just said that system calls are slow. Ring mode, abstraction, Linux and Windows operating systems only run in 2 rings, ring 0 and 3. And then hypervisors run below ring. Here's a picture or an example. So the kernel running in ring 0, applications running in ring 3, device drivers running in rings 1 and 2. The most privileged, so kernel mode really would be running in ring 0, and user mode would be running closer to ring 4. Any questions? Any of that? Closed systems, open systems for hardware people. Open systems are things that hardware is really built around a standard, which then opens it up to anybody to write or create new hardware for systems. That's one of the things that really made IBM compatible PCs so popular, was the fact that anybody could make things for it or even make them. So that's an open system. An example of a closed system would be like an Apple system where it's all proprietary hardware and software, less so now. But like my iOS system, my phone, that'd be a closed system. It's all proprietary hardware. Software, maybe not so much, but certainly the hardware. So the difference between an open system and a closed system, not to be confused with open source, like open source software. That's an entirely different thing. But an open system, hardware-wise, it's created according to standards, IEEE standards, and so I can make my own stuff. There's an example or a picture of a motherboard and the things that are on a motherboard. I don't know how many of the students here have worked with PCs and built their own systems and know motherboards like the back of their hand. For the exam, the system unit is the computer case and everything in it. So going back to this picture, on the top right, that would be a system unit. The motherboard is the circuit board inside of the system unit that kind of controls everything. It's the main board. Has the CPU typically on it, memory slots, firmware, peripheral slots like PCI slots. You can see heat sinks, power connectors, all kinds of things on the motherboard. The motherboard is really all of that. So 2 things you certainly need to know for the exam. The bus. Bus is really just a communication channel between various components in the system. communication between the CPU, memory, input, output, keyboard. There's a picture there where we've got the CPU, the front side bus. We've got North Bridge and South Bridge. North Bridge is faster. It's closer to the CPU. And what it runs is really, its main purpose is really communication with memory. And then the South Bridge, usually more of the peripheral things kind of come through the South Bridge. So the computer bus, North Bridge, also controlled the memory controller hub, connects the CPU to the RAM and video memory fast, directly connected to the CPU. South Bridge, more I/O stuff, input, output, keyboards, devices, mice, things like that get connected to South Bridge. And the only reason why they call them North Bridge and South Bridge is because in the diagrams they're always kind of like this, where one's on top of the other, so north and south. That's no other real reason for why they named them what they named them. Covering a lot of stuff tonight. Hope you guys are having fun. CPU. CPU is the brains. Everything kind of runs through the CPU, just like in your body. Your brain kind of controls everything. The CPU kind of does that for a computer. Everything in a computer is mathematical. If you break it all down, it's ones and zeros. It's flips on, it switches. It's all mathematical. So the CPU does all of that math for us. Rated at number of clock cycles per second. There's 4 steps that happen in a clock cycle, which we're going to get to in a second. 2.4 gigahertz Pentium 4 CPU, which nobody's impressed anymore. 2.4 billion clock cycles per second. That's a lot. A little chip. That's small. But that's the CPU. CPU, 2 parts to the CPU, and there's another diagram with the North Bridge and South Bridge, ALU and CU. So the ALU does the actual math. The CU actually gives the things to the ALU to do. It's the one that fetches instructions and feeds it to the ALU and then sends it back out. So it doesn't do any calculation. The control unit, it just controls instructions. The ALU does the math. That's what's in your CPU. Here's a fetch and execute process. So one full cycle is going back to this. You saw 2.4 billion clock cycles per second. That's this. That's these 4 instructions. So the process takes 4 steps. That's one CPU or clock cycle. So fetch, decode, execute, write. So you can see the control unit fetches it from RAM, decodes it, sends it over to the ALU. The ALU does the execution, then storing it back in RAM. I don't know how accurate that picture actually is, because I don't know if it goes back to the control unit to actually write it back to RAM, but I'm not going to argue with it. I think the important thing to know for the exam is that these 4 steps are one clock cycle. It's not just simply grab it and just do it. There's 4 steps to it. So fetch, decode, execute, and write, and then there's pipelining. So pipelining allows me to write, kind of do it simultaneously, almost. Not really simultaneously, but fetch, executing, kind of fetching and decoding. So I fetch one, it goes to decode, and then I fetch another. So I've got one in fetch, and I've got one in decode, and then I'm executing, so you can see the non-pipeline in the diagram there, the non-pipeline and pipelined. Each part is called the pipeline stage. It just allows more throughput through the CPU. Yeah, so hopefully that makes sense to people. I never get a sense of whatever I'm saying when I'm teaching kind of remotely, if any of it's making sense, but I hope it is. Interrupts. Interrupts make the CPU stop doing whatever it was doing so that it can process the interrupt task and then go back to what it left, where it left off. So CPU stops its current tasks, saves that state because it's going to come back to it again, processes the interrupt or the new request, and then picks up where it left off. Typically, these are hardware related. There's a hardware interrupt. Processes and threads. So process is an executable program loaded in and running in memory. A thread is a child process. Or a process has spawned another process. A heavyweight process is called a task. Process states, new, ready, running, blocked, and terminate. So that blocked is waiting for I/O. If I have a process that the parent has been terminated, it's either called a zombie or sometimes called an orphaned process. A process you can just think of as executions being fed to the central processing unit. The process is the actual program running, but it may spawn a bunch of threads so that it can do multiple things kind of at once within the application. Other things to know about CPUs, you got multitasking and multiprocessing. Those will be the two, I think more key. Multiprogramming and multithreading are important to know too, but multitasking and multiprocessing are certainly two that I would expect to see something on the exam. Multitasking allows multiple tasks or heavyweight processes to run simultaneously on the CPU. Multiprocessing requires multiple processors, so multi meaning more than one, processing multiple processors. Symmetric and asymmetric multiprocessing, it really depends on whether or not I'm using one operating system image per CPU or one operating system for all CPUs. If it's one operating system for all CPUs, that's symmetric multiprocessing. If I have one operating system per CPU, that's asymmetric multiprocessing. But either way, multiprocessing means more than one process. That's a good question. What's a heavy task or a heavyweight process versus a lightweight process? That's a great question because I actually don't know that answer. So if anybody else knows that answer, I'd love to hear it. The difference between a lightweight process and a heavyweight process. So anybody who finds that, please let us know. So I'd like to know too. Multi-programming, multiple programs running simultaneously on one CPU, almost all of our operating systems today. Math intensive could be a heavy weight, meaning that the process itself is math intensive, so they just call it a heavyweight, or is there a certain threshold that has to be met? Okay, so it's just kind of a, okay, makes sense. Thank you, Giovanni. Multi-threading, multiple threads, lightweight processes running simultaneously on one CPU. That would be multi-threading. Other things to know about the CPU, the watchdog timer. So there's this timer that goes on and it counts down, and when it gets to 0, it reboots the system. Every so often, the operating system, the kernel, will reset that watchdog timer so that it doesn't reboot. So if the operating system just stops and it can't reset that watchdog timer, it'll reboot the system. So that's kind of what the watchdog timer is meant for, to recover the system after something goes bad. Complex instruction set and reduced instruction set. Most of us are running on our workstations and laptops and things are running the complex instruction set computers, which is more of a general purpose computer. Just it's not really optimized to run any specific type of function. It's more general purpose. Reduced instruction set computers have a smaller set of instructions for more specialized purposes. So like on my phone, for instance, it's a specialized set of things that need to happen on my phone. I'm not going to hook a keyboard up to my phone. I'm not going to use my phone to act like a server. These other things. Can a watchdog timer be programmed maliciously? I've never heard of that attack. I would doubt it. I would doubt that. But again, if somebody knows that, these are the kinds of questions I like, because you're asking me things that I don't know, that I'd certainly like to hear. But also we get kind of more interactivity, which is good when you're teaching from a hotel room in Memphis, Tennessee. There's nobody here. So anyway, complex instruction set, just your general purpose computer. Reduced instruction set is a CPU that's really designed for more specialized purposes. So your phone, Mobile devices, mobile phones, those will be reduced instruction set computers or CPUs. So, memory protection, so preventing processes from accessing memory space belonging to another. Two primary ways to do this. It's either logically or physically. So process isolation would be the logical method to provide some memory protection for multi-user systems. So this is really only apply, well, it doesn't only apply, but it's definitely required for multi-user systems. What I don't want is I'm running an application and Johnny's running an application. I don't want his application to interfere or be able to access the memory in my application, because I might have different permissions. I might be accessing data that he doesn't have permissions to. We'll talk about this when we talk about attacks. We'll talk about race conditions and some of the other things that maybe we can do to try to get at or attack process isolation. But in general, this is really required for multi-user systems. So logical control that attempts to prevent one process from interfering with another. Object encapsulation allows us to do that. We'll talk more about that when we talk about some of the secure programming things, where it really treats the process like it's a black box. In some cases, we can run a process and no other application even knows that process exists. That would be ideal. Another way to do process isolation is time multiplexing, where I get a set specific amount of time that's dedicated for my process to run, and then nothing else can access that memory space until I'm done, and then you can load another. So 2 ways really to do process isolation: object encapsulation or time multiplexing for the exam. Other ways for memory protection, certainly hardware segmentation. I could use completely separate hardware. That would be even more secure because it's really hard to jump hardware through an application. Virtual memory is another way. Just address mapping to applications in hardware memory, which happens really anyway. So for the exam, for memory protection, we've got process isolation, the logical way, or hardware segmentation. Those are really the 2 primary. Object encapsulation and time multiplexing for process isolation, and just hardware segmentation is using just separate hardware. Other things, swapping and paging. So swapping is really where we copy data from primary memory, which would be my volatile RAM, to secondary memory, which is in most cases is a hard drive. You could swap to other types of media, but in most cases it would be a hard drive. And there's a number of reasons why this might happen. One, I have a limited amount of RAM, and disk is very inexpensive, so I can get a lot more things happening if I use virtual memory than if I was stuck with just what I've got in hardware. I'd say that's the primary reason. I can run more applications. It's obviously slower because I've gotten really even further away from my CPU when I'm using, a disk drive or secondary memory. Really just taking the data out of primary memory and copying it to secondary memory or a disk. When the kernel accesses memory in swap space, so if it's on a disk, let's say that's probably the most common. When the kernel accesses memory in swap space, it's called a page fault. Onto the BIOS. So any questions so far? Am I going too high level? You want me to dig deeper? Making sense? Anybody overwhelmed? Good. All right. So BIOS. The BIOS, basic input output system. This is written to ROM in most cases. Contains code and firmware that's executed when the PC starts up. So as soon as I start my PC, the BIOS picks it up. The first thing it's going to do is do the power on self test. And then part of that power on self test, so the power on self test is checking things, simple tests like memory, hard drive, buses are working, whatever. I've got power like I'm supposed to, no shorts. Just basic stuff. Then the next thing it's going to do is find the boot sector, which contains the machine code for my OS. In most cases, the boot sector is stored in the first sector of the hard drive. And then that will point it to the OS kernel. Once the kernel loads, then it executes the operating system. So in a very basic sense, that's how the BIOS is working. Other things, worm storage, write once, read many. It's not RWs, it's not read and write, it's write once and read many. Usually we'd say this for like record retention and high integrity information. So if I have a bunch of information that I need to archive for a long time, worm media might be good. There's entire cabinets of CDRs or DVDRs or a number of ways to use worm storage. But things to remember for the exam is write once, read many. TPMs. I think my computer has a TPM in it, Trusted Platform Module. It offloads some security features from software into hardware, potentially. Developed and updated by the Trusted Computing Group. It has a processor on a chip that allows some additional capabilities. Usually it's on the motherboard. What we use it for, in a lot of cases, is hardware-based encryption. So my laptop is encrypted and it's done through the TPM as opposed to through software. In most cases, I think software encryption has got a cost of about 4 to 5% of the CPU. Sometimes is dedicated to software-based encryption. So hardware-based encryption, TPM, faster, a little more secure. It also has boot integrity. We use it for that, which protects us against rootkits, kernel bypass attacks. A typical, so one way that we used to attack laptops a lot, and you still can in some cases, if I don't have pre-boot authentication set up in a software encryption solution, or I don't have TPM with, what I could do is boot to other media and bypass the Windows login, and that was a really easy attack. We used to do that a lot. It's harder today because now encryption is a lot more pervasive. The kernel. So TPM, any questions on TPM? The kernel, this is really this is the big dog of the operating system. This runs at ring 0. Everything is associated with the kernel in one way or another. It's the interface between the operating system and the hardware. There's 2 types of kernels for the exam, monolithic and microkernel. The important thing to remember between monolithic and microkernel is a monolithic kernel is one larger, typically larger kernel. If I want to add any features, like let's say I've got a new type of hardware that I want to introduce to my system, it would require me to recompile the kernel. I would have to add those features into essentially a new kernel. Whereas the microkernel is a modular kernel, and I can add functionality just by adding kernel modules, and that's what a Windows 7, 8 system is, a microkernel system. Where I can add functionality just by adding adding kernel modules. I don't have to recompile the kernel, which I couldn't do anyway on a Windows system. Things about the kernel that I think are really important. Certainly it runs the reference monitor. Now the reference monitor truly is a core function of the kernel, especially how it relates to information security. It mediates all access between subjects and objects in the system. It's always enabled, can't be bypassed. Hopefully those things are true. In a secure operating system, that would be true. Types of permissions. I should have maybe made more. I didn't realize I was going to go through this so fast. Users and file permissions, types of permissions depending on the file system being used. In Linux and Unix systems, we have typically 3 types of permissions: read, write, and execute. They can be set separately on owner, group, or world. If you do an ls -la on Etsy, this is what you'd see. The first, so you see DRW on the far right, let's say of ACPI, DRW. So Those are the permissions for the D is directory. The read, write, execute would be the group permissions. And then the world permissions. So owner, group, world, sorry. I'm trying to keep it. And then Windows permissions. To NTFS, we have read, write, read and execute, modify, full control. Most of us in Windows have right-clicked on something and select permissions and gone to the security tab and seen what kind of permissions we can assign to users. And that's it. So we actually got through that a lot faster than I expected. But I also don't know how well I covered it for you guys. It seems like I'm a little bit off maybe tonight. Any questions on anything that we covered? Do you want me to go back and touch on anything else? So we do have time left. If not, then you get a half an hour back, and we're not going to send easy as pie. That's right. Our cake. Wait, here we go. It's just going to require a lot of memorization. That's true. The security models will take some time. And honestly, I think the security models are kind of a pain in the butt because to me, they just seem sort of useless. I mean, I like the concepts behind them, but you just don't use them. So it's one of those things that purge. Seem very large government-based. Yeah, well, and government did drive a lot of the conceptual things, which I think are really good. It's just, it's hard to apply it. Well, everybody gets a half an hour back. We're not going to send you a bill for it. That's good. Usually what they're, yeah, exactly. Yeah, those security models, you would only see those in governments. And the modes of operation, those first three modes of operation, you would only see those in government operation. You'd only see, dedicated, system high, and compartmented really in government. The rest of us use that multi-level or the State Department or Hillary Clinton's homebrew server, maybe. All right, well, what we're going to do next week is Tuesday, we're going to pick up virtualization, distributed computing. That'll be pretty quick. The challenge next week is I want to slow down a little bit on encryption because I really do think that applies to our day-to-day what we do. Encryption's a big deal. And then we've got physical security also on Tuesday. Physical security is also a big deal. But we don't have to go, it doesn't go very deep. It's talking about some of the preventative, detective, and controls that we might put in place, really around perimeter security, layered defense, and stuff like that. So that should be fairly straightforward. And then following Tuesday's class, we will have a quiz. We'll spend some time on that quiz because that'll drive home the things that we learned tonight. So homework for Tuesday, continue reading through chapter 4. Go through it again if you have time to go through it, a couple times. I hope that there are some questions. I do like the questions. There were some questions tonight that I didn't even know the answer to, which is good. So thank you guys. Have a good night. I'll be on probably a better game on Tuesday too. So thanks guys.